Dear students, in this section 2.4, really we have an important section. So more detail, more pages, and need really concentrating. In this section, I need your all or fully concentrating, your concentration. So please focus on the each word that I am mentioned here. First of all, limit involving infinity means that x approach to 0 or to infinity and minus infinity. And the second word or the second concepts, we have asymptotes. Okay, we have asymptotes. Asymptote means that's something that you can sometimes to intersect your graph with it. Okay, so we are going to talk about this one by one. We are going to talk about the Theorem 12, which is tell us about the c or x approach to infinity and or x approach to minus infinity. So instead of number, we have an infinity and minus infinity. You know, when we have some numbers, for example, we have a 1, we say x approach to 1 from the left or right. But when we say x approach to infinity, means that we have a function here, for example, like that. We have a function, but x approach to infinity. There is no number, okay? Or maybe x approach to what? Approach to negative infinity. That's our idea. So here we have limit of x approach to, for example, infinity, which we have 5 plus 1 over x. And you know, we can distribute, you know, then we can distribute some x approach to infinity, the limit, distribute the limit over the addition. We have this property before we talk about this one. And you know, the result of the constant function is the constant, and 1 over x means that you have 1 over x means that we put 1 over nearly infinite numbers. So look, here's the curve. Here's the curve of our function. I'm going to show you by the graph. X approach to infinity. Look, we are going to infinity. Look at the graph. The curve is going to where? Over y-axis. From the beginning, from the largest to what? To the smallest, nearly to 0. So in other ways, means that put 1 over 100, 1 million, 1 million, and go on. So you get something very, 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 very small, which can be approached or accounted to be 0. That's why we say 1 over x is equal to 0, and the result will be 5. Okay, dear? That's about the first. How about the second? We have what? The first example. The second example, we have limit approach to x to approach to minus infinity, pi over square root of 3 over x squared. Okay. You can solve this one by two methods. In your lecture, he solved by the he analyzed by the method, and I'm going to directly I'll skip one step for you. So pi and square root of 3 is number, so it remains 1 over x squared, where x approach to what? Minus infinity. And you know the graph of x squared. So when you are going to negative infinity, the curve is going to where? From the largest going to smallest, nearly to touch the 0. Y is equal to 0 here. So that's why we say is equal to pi square root of 3 multiplied by 0. And again, you have a pi, again, you get the 0, the result. Okay, that's all about the first page. Now, here in the second page, okay, here in the second page, we are going to talk about another important things here. You can say what? Limit at infinity at infinity of a rational function. What's the rational function? We see that we have a polynomial over polynomial, polynomial over polynomial, another polynomial. Okay, x squared, not something like that, to something else. So here we have in the example 3, when I'll give you some how do you say some trick here. We have three cases, okay, when it's a rational function, and you hear that this we have three cases. We have polynomial over polynomial. For example, we have x squared plus 5 over x minus 1. Okay, maybe that you call this one by n, this one by m, the degree, 1, the exponent. Maybe n or up greater than lower. Okay, up greater than lower, or maybe up less than lower, or maybe they are equal. Okay, if they are equal, it's equal, the result of the limit will be equal to the coefficients. If upper is less than, so you get what? You get 0. Yeah. If upper is greater, you will get infinity or negative infinity. It depends. Okay. What do you mean by this one? For example, I have the limit x approaches to infinity, 5x squared minus x cubed over 2x squared minus 1 over x squared minus plus 2. So in that case, we have a polynomial over a polynomial. But here, x is greater than what? X is greater, upper is greater than lower. So I get what? I get infinity. For the next example, we have the same example, 5x plus 2x minus 1 over, let me square, over x square plus 2. In that case, they are what? They are equal. Okay, they are equal. So it's equal to what? 5 over 1. Let me 2. So I say 5 over 2. Why? Because I say is equal to coefficients. If it's a 1, you say just 5. If it's a 5 over 2, say 5 over 2. Even they are not arranged. Even they are, if this one is here, it's okay. Depends on the maximum degree. Okay. Number 3, if x approaches to infinity, to, for example, 5x squared minus 2 over 5x cubed minus 3. So in that case, because the upper is less than lower, I will get 0. Okay, case number 2. So that's all about the rule about for what? For rational function. For rational function. That's why he say that try to this example, what happened to the degree of denominator is less than or equal to the degree of the denominator. So numerator and denominator. So here's they are equal, so is equal to 5 over 3, the result. You can directly put it down. And here we have what? The denominator is less than, greater than upper, so is equal to 0 directly. Okay, dear? That's all. Now, because limit is going to infinity or minus infinity, if you get here, for example, look at here. If you get some result, now this result, this value, if you get value, if you take a limit to infinity or minus infinity and you get a value, this value means that horizontal. So now we have horizontal asymptote. Asymptote, as I told you, is دركنار. Okay, so if you take anything in other ways, if the degree are equal and you get some number, this number is your vertical horizontal. Vertical asymptote. Vertical asymptote. Okay, and it's okay in the vertical very sorry, in the horizontal asymptote. Stuni. Horizontal. Okay, and it's okay if the graph intersect your horizontal asymptote. لا در کناری آسایی اگر نقشکت در کنارک ببره. But for vertical you have something else. Okay, that's all. How about this case? x approach to 1 over, you know, this point are asymptote, you can see. Okay, the result is equal to 0. So 0 is your what? Is your horizontal asymptote. Here's 0. Y is equal to 0, we mean. Y equal to 5 over 3, we mean. Here's y equal to 5 over 3. Okay, dear? So that's the definition of what horizontal. So the definition of horizontal depends on x approach to infinity or minus infinity in there. And for example, you have what? You have something like that. Okay, dear? That's all about what you say about the horizontal asymptote. Okay. Now, how about this function? How we solve this limit? Also, you have something like that in your exercise, I think. So let me solve this one for you. He say find the horizontal asymptote. Or maybe he didn't say anything. He say find this value. Okay. For what? X cubed minus 2 absolute value x cubed plus 1. Now you know absolute value. If I am going to positive infinity, x will be what? The value in the absolute value of x going to infinity, or means that going to positive. So I'll get x cubed plus 1 x cubed minus 2. And you know this is the sum between two cube, but here we have what? We have absolute, I have infinity, and I told you this is a fraction, polynomial over polynomial. So the exponent or the degree are equal, so you can say is equal to coefficient over coefficient, which is equal to 1. Okay, how about x approach to negative infinity? And you know numerator is the same, but denominator will change to something like that, and it's equal to, you know, also coefficient over coefficient. So you'll get what? You will get 1 over minus 1 is equal to minus 1. So this is the result, and you can say we have 2 because I have two value, so I know 1 and minus 1 are asymptote. Which asymptote? Which type? Horizontal. Why? Because I got value and I got another value, b, we recall as a b. So here's this, the canal. Maybe the graph as you have, I don't know, maybe the graph, look, here's the graph. I don't know really how to scale this graph, we need more work. So here's, in this one, he couldn't cross the vertical, it's okay, but sorry, horizontal, but here crossed or intersected, it's okay. It depends, as I told you. Okay, that's all about example 4 in your page 3, 2.4. Now I'm going to what? I'm going to talk about something else. I'm going to talk about this formula. Look, limit approach to infinity of sine 1 over x. Okay, first of all, I'm going to really to solve the part B, then later I'm going to solve the part A. Why? Because there's something I think it's easier to understand. So example 5, page 3 in section 2.4 in your lecture note, part B. We have x approach, will be just infinity. Okay, x sine 1 over x. Now, before we know, we have sine theta over theta, where theta approach to 0. You have this formula, it's equal to 1. But here something changed. This is infinity, not 0. And this is the sine 1 over x, not x. And where's x? There's no x. So what can we do? How we solve this one? Okay, there is something we say substitution. How? I say let t be 1 over x. Why? I want to fix this one. So sine will be what? If I put here, so sine will be what? Sine of t. You know why? Because we change 1 over x to t. So now I have x is equal to what? From here you can say x is equal to 1 over t. Am I right? So this is the x, 1 over t. Okay, we change this one to that one and this one to that one. How about x? We have x approach to infinity. How about now x is not x? So what we have? If x approach to infinity here, t will be x approach to infinity. I get what? I get t is approach to 0. Why? Because if I put 1 infinity here, so 1 over infinity is equal to 0. So that's why I say t goes to what? To 0. Now, just order what you did. Just order. Look. It look like this one or not? Yeah, it look like this one is equal to 1. That's all about the example. Part what? Part B. Just going to infinity, positive. The same thing is true for what? For negative. So you get the same value. How about now part A? Part A, we say that I have this one. Now it's time to change. To change what? T to be 1 over x. So I get what? Sine of t. Okay. So or you can without any change, just put it directly. Say x approach to infinity. Put it directly. Means that sine limit of x approach to infinity sine 1 over t. I can say what? I can say if I put infinity here, I'll get what? I'll get 1 sine of 1 over infinity, which is equal to sine 0, which define is equal to 0. That's also why I should change it. Nothing to change. So it's easy and you get the value. But in your lecture, you change it to something else. You don't need it. It's okay. This is the very important part of the, what you say, you can say in the limit and horizontal asymptote. Forget about example 6. You talk about the sandwich theorem for the infinity and minus infinity. Okay. Now we are going to what? We are going to the limit. Look at the limit. What will happen to the limit? Limit can be go to something else, somewhere else. And also we have something, another type of asymptotes. Oblique, lar, slant. Sometimes you can hear the slant, yeah. So what do you mean by the slant? What's the oblique asymptote? You know that kanar. Okay, in this page I'm going to talk about two things. Example 7 give us some idea that if you get indeterminate form, some form like that, if you say x approach to infinity to some function and you get infinity minus infinity, this is also indeterminate form. Which means that bari nadir. Okay, we don't know. Is good or not? Is bad or not? Is has got result or not? You don't know. So in that case, if you are going to infinity and for some function and you get something like that, you should do something else. You can't decide, say, well, I is equal to infinity or 0. Kafir, what do you say? Okay, you cannot mention that. Okay, so we say that x approach to infinity for x minus x squared plus 16. If I put infinity, I will get infinity. If I put infinity here plus 16, I'll get infinity. So we cannot decide. So just try to what? Try to use, this is negative. Try to use conjugate. How? How'd you keep on? Conjugate. Why? Because you have a negative here, so I can say decide directly. X plus. Okay, that's all. Now for the first part, we get what? X approach to infinity. For the denominator, we have x plus x squared plus 16. How about for here? We have two things like x squared minus x squared plus 16. That's all. Okay. Now you can multiply this to here. Now x squared and x squared will go. So it remains limit x approach to infinity 16 over x plus x squared plus 16. Now you have you can decide is equal to 0. Why? Because I have rational function Here you have just 16, here you have 1, so the power of here is greater than here, right? So you can see is equal to 0. That's all that you need to know about the graph, the limit. Okay, so do not forget about why we multiplied by conjugate, because I got indeterminate form. What's determinate form that we talked about? We talk about infinity minus infinity. That's why we multiply by conjugate, then we solve it together. Okay, here we go. So what else we need to talk about oblique asymptote? We have two conditions to talk about the oblique. First of all, we should take we have a fraction or rational function. Okay, the second, I mean, the power degree should be more than 1 to the power in the denominator. Look, x square over x. Okay, x cube over x square. Otherwise we have no oblique. Maybe we have something else. It's okay, but here we have no oblique. But now I'm going to talk about oblique. That's why I say the condition should be like that. Fraction, the numerator's degree should be greater than the denominator degree by 1. Okay, then we will divide long division. We will do the long division, and we get something as a function and remainder. Then the remainder will be our the remainder should be go to the r, should be go to the 0, I think, and the other should be sorry, go to the let me see, yes, go to the 0, and the others should be the linear function. Now, so I know it's complicated for you, but I'm going to apply or satisfy these conditions together on this example. So example 8 in page 4 in your section 2.4, we have what? Find the oblique of this one. Okay, find the oblique asymptote. Okay, now first of all we have a fraction, okay, or rational. Yes, the second degree is greater than to the degree by 1. Yes, 2 1, it's okay. The third one, we should we should take r to be 0. Okay, how? Now do not forget about long division. So x to power 3, I told you should divide it minus 4. So I need 1 over 2 x. Why? Because 1 over 2 multiply 2 is equal to 1. X multiply x is equal to x square. So 1 over 2 multiply 4 is equal to 2x. That's all. Now we will divide and we subtract. So this one will change from positive, will change to the negative, and this one will be positive. So negative x square, positive x square will remove, and it remains 2x minus 3. Okay, that's all. 2x minus 3. And there's a 1. We can see plus 1. 1 multiplied by 2x, we get 2x. 1 by 4, the same. So by addition, so we will change the direction, the sign. So I will get what? I get 1. So now here's the division, d, and here's the remainder that I told you, r. So what will happen? X squared minus 3 over 2x minus 4 will be equal, so f of x will be equal to what? Sorry, will be equal to 1 over 2x plus 1. Okay, this is the linear that I told you we should have a linear function. This is the linear plus remainder. What's the remainder? 1 over 2x minus 4. Okay, this is our remainder. Now we are going to take x to be infinity or minus infinity to this part, to r. Okay, and I should get 0, otherwise it's not slant. We have no slant. So if I took the limit for just the remainder r here, I'll get what? It's x approach to infinity, 1 over 2x minus 4, and you know this will be 0. Why? Because numerator is greater than denominator is greater than numerator. Up is less than lower, so is equal to 0. I'm going to repeat it for you because I know you didn't understand directly. F of x is equal to x squared minus 4 to x minus 4. So in that case, if you want to oblique, you should have a fractional. Yes, I have a rational. Numerator is greater than the denominator. Up is greater than lower by 1. Just 1. Okay, yes, you are right. And the third, you need a long division. Which can we do it here? 2x minus 4. We have x squared minus 3, and we will divide that here by 1 over 2x. Multiply, we get x squared minus 2x. Now we have 2x minus 3 and plus 1. I will get 2x minus 4. We'll change to division and I'll get 1. This is 1 will be our remainder. This will be the linear or division part. So f of x will change to what? From here we'll change it to 1 over 2x plus 1, so our linear L, plus remainder, which is equal to 1 over x 2x minus 4. And the remainder we will take x approach to infinity or minus infinity for the remainder, which is equal to x approach 1 to x minus 4. And here should go to the 0. So you can see if I put infinity here, I get 1 over infinity is equal to 0. So our slant asymptote is g of x, will remain as a g of x, 1 over 2x plus 1. So it means that here's plus 1. Okay. This is our slant or oblique asymptote. As you can see, here's this graph. This is our oblique. Okay, that's all. Okay, dear, that's all about the slant. What do you say? Slant asymptote. Now, later in the next video, I'm going to talk about infinite limit. What do you mean by infinite? So limit at infinity. Limit at infinity means that x approach to infinite or minus infinite. But what do you mean by limit? Infinite limit. Infinite limit. We mean something, any number, you get infinity and or minus infinity in the result. Here is in the approach. Here is in the result. Next video I'm going to talk about this part.